So today we're going to be talking about section 6.2 that has to do with free energy. And free energy is very important in biology because the main reason why we learn about it is that whether or not the change in free energy has a certain characteristic, we will find out, helps us determine whether reactions will occur spontaneously or not. So when we talk about free energy, it's also known as Gibbs free energy, so we call it the G in an equation, and typically biologists are concerned with the delta G, or the change in free energy. That free energy is the portion of a system's energy that is available to do work. And the reason why we care about the change in free energy is because that usually tells us what the energy change in a particular reaction will be. So that change we call the delta G, like I said, and you can calculate it by taking the final energy minus the initial free energy, subtracting them, and that gives you your delta G. In biology, we care about the delta G, like I said, because we want to know whether reactions can happen on their own or not. And only processes with a negative delta G are spontaneous. And when we say spontaneous, that means that those reactions can happen on their own without the input of additional energy. So to have a negative delta G, the system must lose free energy from the initial state to the final state, meaning that the final state is more stable. So the delta G, when we're talking about it in chemical reaction, really refers to the instability of a system. How likely is that system going to trend towards becoming more stable as opposed to less stable? During a spontaneous reaction, the free energy decreases and the stability of a system increases. So one thing that's important to remember is that when we talk about spontaneity, it's more, you should think about whether or not something will react. A lot of times, based on how we use the word in the English language, a lot of people think it means it's going to happen rapidly or quickly, but that's not necessarily the case in biology. A spontaneous reaction just can happen on its own. But you've probably learned about enzymes already and how those can help our reactions happen quicker. A lot of times these reactions happen too slowly, even though they are spontaneous, to really go quickly. So that's going to be an important thing to remember when we're talking about spontaneous change. These are some examples here of reactions that are spontaneous. So in all of these reactions, the free energy in the system is decreasing and the system becomes more stable, and the energy that's released is available to do work. So one great example that we've already talked about is the example of diffusion. So the molecules, as you remember, will naturally diffuse from an area of high concentration to an area of low concentration. And because that reaction has a negative delta G, that's going to happen naturally. It doesn't require any additional energy. That's why diffusion is an example of passive transport, because we know you don't need any extra energy to make it happen. It will just happen naturally. At equilibrium, forward and reverse reactions occur at the same rate, and that is the state of maximum stability. So processes can only be considered spontaneous and can only perform work when they're moving toward equilibrium. And any change from equilibrium will have a positive delta G and not be spontaneous. So if it's not moving towards equilibrium, if it's moving in the opposite direction, then that's when you're going to need to input some energy in order to make the reaction happen. When we're talking about free energy, the reason why we care about it is in the chemistry of life, or in biology, the way free energy works affects metabolism. So like I said, all of our metabolic processes have to result in a negative delta G in order to happen on their own. But remember, that doesn't mean they'll happen quickly. So we have two different types of reactions. One is called an exergonic reaction, and these are reactions that release energy. They occur spontaneously and they lose free energy as the reaction occurs, so our delta G is negative. So because the delta G is negative, they're spontaneous. And these are reactions that occur, like I said, on their own. They don't require any extra input of energy. This top picture, which we'll look at in a bigger version in a second, shows us what an exergonic reaction looks like. So you can see At first, the reactants have a lot of energy available to do work. The products have much less energy available to do work, so there's been a loss of free energy. If you subtracted the final from the initial, you'd get a negative number, and so the change in free energy is less than 0. It's a spontaneous reaction. Exergonic reactions, on the other hand, require energy. They absorb free energy from their surroundings, and they're considered non-spontaneous. And when you look at the delta G, you'll see that that difference is positive. So the amount that is the change in free energy, that's actually the amount of energy required to have the reaction occur. So this is a non-spontaneous reaction, and you can see the reactants have much less energy than the products. We need an input of energy in order to get to the products, and because that delta G is greater than 0, this is a non-spontaneous reaction, so it will not happen on its own. This is important for our study of biology because in isolated systems, reactions will eventually reach equilibrium and can do no work. However, our cells are considered open systems, and they should never reach equilibrium. A cell that is at equilibrium is dead. So you don't want your cells to be dead, and that is why metabolism is one of the requirements for life. And the reason why cells never reach equilibrium, even though, as you know, they're always striving to get to that point, they never reach equilibrium because things are always diffusing in and out of the cell. There's constantly proteins, chemicals, molecules, all kinds of things moving in and out of the cell, and as long as that's continuing to happen, the cell will never fully reach equilibrium and will continue to process things in and out of the cell and keep it alive. So the way that most reactions in the cell work is there are typically catabolic pathways that release free energy in a series of reactions. So the product of each reactant is the reactant for the next. And this kind of prevents the system from reaching equilibrium because once something's produced, it gets used up right away for another reaction. And this is also part of what helps keep the delta G negative in most cases, keeping things more spontaneous and able to happen on their own. And that's where we'll leave off for now. Thank you.